as you are actually, not violating those kinds, like what is the noise margin, what is fanning, what is fan out, what is drive strength, all that we will discuss. This becomes really important if you are going a little beyond actually coding tomorrow in the company. For example, you are only purely doing Verilog coding or VSDL coding, then you may not really bother about all this. Okay, but let's say you are not only doing Verilog coding of it. Okay, you are also getting into the backend. Then you need to talk about, so you have taken some backend library and plugged into your tool, which is generating the final netlist, final layout. Then what is used by drive strength? Where I should choose actually higher drive strength XR gate, where lower drive strength XR gate will do. All these basics will come in fan and fan out. Okay, we will do enough design exercise. So you have to bear with me for a few classes. You should not think why again we are learning all theory. Okay, I am removing all whatever general stuff, but very essential theory, very important design fundamentals I got to tell you. Okay, they are very important. Okay, so yeah. The next we will talk about logic, logic families. So we will not get into all details, like we will not do general distance course here, that all the parameters we will not. We will have a brief understanding about all. Mainly we will try to look in different dimensions. Okay. Tomorrow it is quite possible that some of you may be working on the FPGAs, where your role is not only write a VLSI code and put it into FPGA, synthesize the FPGA, but also you may have to interface the FPGA with an outside ADC or outside DAC. Okay, so the ADC, let's assume 8 lines are coming to your FPGA pins. If you look into the ADC data sheet, it will be written that it is actually DDR lines, double data rate lines. So it means data is coming on both rising edge and falling edge. Okay. Now you should know how to configure an FPGA pin also in the DDR mode. Okay. You should also know what are the different voltage levels that ADC chip is actually giving. Differential line or single-ended line. If it is differential, what is a common mode voltage and what is the differential swing that you need? Whether that your FPGA pins are compatible to that or not. All these you need to know. You got it? So we are going to talk in that perspective about the logic families. Okay. Not in the kind of how NVIDIA is realized by TDL. That we will not do. That is what we have done in the digital course. Okay. Oh, because CMOS anymore is our friend, and today what entire ASIC backend is with CMOS variants. CMOS we will learn in depth. How to realize NAND gate, XR gates, combinational, sequential, D flip-flop, everything about CMOS we learn. But remaining all we will not learn like design point of view, only interface point of view we will learn. Okay. The next we will be talking about I can't check now. But let me use it. Okay. Okay, so we'll be talking about next combinational logic circuits. I will quickly maybe give a half an hour kind of overview, like whatever you learned in your postgraduate, undergraduate courses about combinational logic circuits. But more focus I will give in actually implementation perspective. Okay, like when combinational logic circuits, what is the speed criteria, what is the glitches, why glitches do come, okay, and how do you overcome all XYZ aspects. Okay. Now sequential logic circuits. This is a more important topic for us. We would learn about realizing what is called state equations, like how your combination logic circuits will have y is equal to a b bar. Okay, your sequential logic circuits will have actually qn plus 1 is actually a function of qn. Qn happen to be the nth clock cycle output on a D flip-flop. Qn plus 1 happen to be n plus 1 there. So when it comes to sequential logic circuits, we would like to look at a kind of Boolean expressions which also involve states in them. That becomes the basic for actually state machines. Okay. Formally, when you represent the state machines, you need actually those basics. So we will learn them. Then next we will talk about state machines. So having learned sequential logic circuits and state equations, state machines become pretty simple for us. Okay. The next, when we talking about high-level design aspects in digital system. Please, you can ask him to correct. Yeah, please. No problem. Okay. So, I'm talking about next high-level design aspects in digital system. That's what. So now, whatever so far we have done, bits and pieces we learned, we try to put them together. Okay. We learned about differential pins. We learned about voltage standards. We learned about fanning, fan out, etc. We learned about the Boolean equations. So now high-level design aspects in a digital system. When you say digital system, you will start with a kind of maybe an ASIC or maybe an FPGA. It has to talk to outside world or some protocol. Okay, some bus standard. So we get a kind of full picture when you are designing a digital system. What all issues will come. They will only get issues only, not solutions. Okay, that's what. The next, signal representation, digital fixed and floating point. So actually, this topic, whatever mentioned here, will be covered here. Okay, even though I felt it's here, but little bit I will cover here. Okay. Next, dynamic range and quantization noise in signal. So these are also related to this only. Like you have 16 bit. 16 bit, each bit will represent 6 dB. What do you mean by that? We will discuss about it. Okay, because it is quite possible that so many job profiles in VLSI would require a tight working with the ADCs and DACs. Okay, working with ADCs and DACs could be on chip or could be off chip. But whatever it is, when you have to work with ADCs and DACs, you should know the signal processing meaning of every bit that you are handling. So we will have necessary background for it, but I will not clutter with all the equations. Okay, but end equations are really important for interview point of view. Okay. At regular intervals in my course, I would like to flash some question papers of popular VLSI companies to show what kind of questions they are asking and how those questions we want to pick, indirectly those questions content, how we want to actually, bridge in our course. Okay. Yes. Okay. So next, we are talking about what, of course, this content is open. You can always suggest, I would like to add further topics. I may not delete, but whatever you said is really logical fit, I will add additional topics. Okay. Then next, we'll talk about control data path based design. So in a way, this topic becomes a little bit continuation of basically this one, high level design aspects in a digital system. So what do you mean by control data path based design is, see, we learned on one side combination logic circuits. We learned multiplier, we learned actually what do you mean by MAC, okay, and all this. So now when you want to implement any algorithm, okay, that will be much more complex than a simple multiplier and MAC. Okay, so like chaotic algorithm, or maybe some adaptive filter algorithm, or maybe any algorithm. Maybe it's an encryption algorithm, decryption algorithm, encoding algorithm, MP3 decoding, anything. So when you want to implement an algorithm, finally you have to get into RTL implementation style, register transfer level. How your data is moving from input to output among various registers. And those registers are controlled by a state machine. This is nothing but control data path. Control data path is a little abstract, technically critical word which people use in algorithms. Okay. But let me tell you, once you understand the bits and pieces and general implementation style of control data path design, any algorithm, whether it is given in C or whether it is given in MATLAB or it's paper-based design, you know how to tackle that. Your implementation will be VLSI friendly implementation. Okay. Now, an overview of bus standards and protocols. So since, as I said, this module is aimed for giving a full overall glimpse on all the issues in VLSI, major issues today in VLSI verification are actually with respect to buses. So I'm not only limiting to design, this module is trying to give some background for the people who are aiming for verification first. Today, if you see all the designs across the industry, they are SOCs. Okay. What is an SOC? System on chip, isn't it? What do you mean by that really? System on chip is of course an abbreviation of expansion of that SOC. What actually you mean by it?
Everything is not system.
Yes, the simple English meaning, if you look at it, is like a complex system is going on a single chip. That's why we call it as system on chip, isn't it? But let me tell you, in industry, point of view, when we call a flow as a system on chip flow, and when we may not call system on chip, when we call only ASIC flow. It is like this. Any silicon design flow we call it as ASIC. Okay, but ASICs, when that involves IPs from different parties, then industry calls it as system on chip. Okay. For example, let's say I'm, if you look into NXP, which is Philips Silicon division, where, like for example, one IP is coming from ARM, which is ARM core, another IP is coming from, let's say, USB 3.0 from the farm company, Ethernet IP is coming from some other, okay, and some multimedia IP is coming from Broadcom, let's say. Now all this put together, you are now taping out one chip. Then this is actually system on chip. So industry sees in that way. But challenge is, when you are building system on chip, these IPs need to talk to each other in a what is called a compatible way, isn't it? Or you need to have cross-platform compatibility, or in simple words, interoperability. Like when you have an IP, you should not demand that your IP has an exclusive interface to it. Then it is difficult to talk to your IP. So what people are doing, every IP will follow some standard bus protocol. Means what? System on chip, the buses are going to play a crucial role. Okay, so all the buses which I have brought out here, some are very simple buses which like SPC, and some are very complex buses which we may be touching upon basics of it. But the idea is to tell you in this particular session that what are the different buses. When you start learning about a bus standard, what are the issues you come across? What are the different categories of buses? What is the master slave bus? What is the crossbar? Okay, all these kind of things we will talk. Okay, basics. So, continuation of this, this topic, in our last module, which is verification module, you would find enough, verification assertions written on specifically on bus standards. See, out of all these bus standards, few bus standards happen to be very popular in, today SOC verification. So, those things will be giving more emphasis in our Verilog model, system Verilog model, final verification. But apart from that, even for designer also, it is very important to know basics of the buses. Okay. I'm sorry. Next, we will be talking about design issues in FPGA-based systems and ASICs. Okay. Again, I would say this is a kind of continuation to the topic that we started about high-level design aspects in discrete systems. Okay. Something like case studies we will do. Okay, we will take a case study. Somebody is designing a board and somebody is developing firmware for application. So, what are the various aspects of application which are dictating the features in hardware and software? We will talk in that perspective. Then, throughout our course, we will be doing small digital design exercises. Okay. So, I will tell like this, in the beginning days, it will be related to noise margin calculations or fan in fan out based drive strength based calculations. Then, our exams are always open book. So, when we ask you to write exam, the related material will be downloaded into the PC and you will be given access to the PC. For example, I have explained you about Spartan 6 FPGA IO standard as a part of our interface standard session. Then, when I give you a question paper says, in Spartan 6, is LVDS supported? If so, what is the common mode voltage and what is the differential swing required? Got it? We are not expecting to by heart and do it because nobody needs that also in the industry that you by heart those numbers and tell it. Okay? You should know how to browse the data sheet of that and you should know which table to refer and what is the answer to get. This is what the kind of design exercise we are going to do. Okay? Yeah. Then I would just quickly give an overview of other modules and go to our first session. Okay? Now, this module is about introducing the VHDL and digital design fundamentals. Okay? Lot of things related to depth concepts about RTL coding or performance analysis, speed analysis, area analysis. I move to the next module very well. But let me tell you frankly, they are independent of VHDL coding or regular code. Once you have done some coding, okay, for particular requirement, whether it is VHDL or regular, when it comes to static timing analysis, finding out the critical path or improving the speed by pipelining is nothing to do with the VHDL Verilog. But since there is a kind of more inclination to Verilog usage across this one, I wanted to increase the number of hours under Verilog. So I moved all that content here. So this module will only talk about syntax of VHDL and only to control data path design, which we discussed there in the context of VHDL, how we do it with a couple of small assignments. Okay. Then in Verilog, as I said, we will learn about complete Verilog syntax. We will learn all the concepts and how VHDL gives one requirement and how Verilog can give it. Let's say rising edge D flip-flop with enable. Okay, how are you coding VHDL and what way you have to code in Verilog. That kind of comparative picture you will get here. Then we will talk about speed-wise aspects like setup time, hold time, clock to output time, how they dictate basically your performance of the circuit. If it is ASIC flow, what kind of inputs you get for optimization. If it is FPGA flow, where to optimize. All that you will be studying. Then we will also talk about applying all these principles in the Xilinx tool flow. So we take Xilinx software, Xilinx IC, and in that take one example, do static timing analysis. It will show that this clock to this clock you have maximum latency because of maximum delay, because of which your maximum clock frequency is only 100 MHz. Then we will apply the technique that we learned to improve the speed. Okay. And second, let's say we take a bigger design and that design has 10-15 paths. And out of those paths, one path is actually really critical path for you, and remaining paths, even though they look paths, that the data is not changing in them. So they are called false paths. So we will learn how to give the information to the tool that you optimize this path only. You ignore these paths. All this we will learn in the Xilinx tool. Let me tell you, only tool to tool, how to enter, where to enter, which button to click, which menu option to, that will only change. Okay, principles remain same. Got it? We will give more focus to various tools, in this module. Yeah. The next, you will also basically learn how to use on-chip debugging tools, using JTAG. Okay, write some code, verify using chip scope, observe the results, what are the limitations of the approach, all that we will learn. Of course, we will also learn about area aspects, power aspects, all that. Then this module is about making people, to work in the back end side. Okay. The last two modules are about actually for the front end side. In the VLSI, where you want to do whether front end design or front end verification. Okay. Now you may argue, sir, verification means we need system verilog. Do we still need verilog and VSDL? You need it. The reason for that, system verilog, people are writing for verification. Okay. Assertions and all they write. But what you verify need again verilog mode. Okay. And today, let me tell you, in industry, the jobs are not clearly bounded like that. Okay, this is verification, this guy is the design. It's not that. When you are doing verification, several bugs when you notice, and the cause for this bug is very clear, then you have to fix the bug also. Got it? Example is something like you notice that one place it is as I said control data for design. Enable is going to the all. Okay, one place enable is not going. That's a bug. Okay, as per the design spec, enable should go to all the kind of flip flops in the design. Then you have to fix there itself. So you should also have knowledge on VHDL and Verilog, because system Verilog internally is going to instantiate VHDL and Verilog modules. And so many times verification team, especially in India, they are not only doing verification, they are doing fixes also, bug fix also. People don't expect that you start doing verification. Let's assume that you notice the bug right in the first 1 hour. Does it mean that you put that to actually design and wait for solution to it? No. Very major bug only, which is not apparently visible, okay, which you cannot fix it, will only be reported to design team. You got it? The reason is not known actually what is happening. They only will report to this. Okay. There are so many things we will discuss actually during course of time. For example, like this. See, now somebody has written the code. They have written the code. One portion of the code, with the rising edge triggering. One portion of the code with falling edge triggering. Now, where these two fellows are talking, there the what is it called, the clock time, okay, which is available. The window that is available is very small. Now, this is a bug. Now, this bug people don't expect that you report there somebody. You should know what is the solution for it. So that's what I'm saying. So this module is actually for backend. Purely for backend. If somebody don't keep interested, I don't like transistor equations and all of that. No problem. Let me tell you, most of the jobs are actually front end or verification related, not backend. But backend verification people are very highly paid and they are very reputed jobs. Okay. But maybe in the beginning also you may not get any backend job just like that. Okay. You may be put into backend verification. So in the means in the initial days you will have a Verilog code. You will synthesize it. You will get a netlist. You do timing simulation. Or you do some corner case analysis, but not more than that. Okay. However, this module is able to give all the issues which come in a CMOS based backend design, like CMOS cell design. Okay. So you are like working for a company where you are designing your own cells, or you are actually having some cells from some other third party. You are optimizing them, or you are not even optimizing. You should know how to use the optimum cell out of what is given. Then when you get a cell library, you get actually same XR gate 5 versions of it you get. Somebody says higher area, higher power and more fan out. Somebody says lower area, so you should know which one to plug. At least you should know what to tell, okay, to the tool. So this is what we will be doing, okay, in this module. So next module is about writing, this is an introductory module I can say for verification. So there are 2 levels of verification modules that we are offering. One is introductory level, it means it will talk about very simple verification practices, which are there from I should say 25 years, at least 20 years. Okay, indirectly they are there, like using assertions in Verilog itself, using assertions in VHDL itself, using file reading and file writing kind of thing, okay, to give appropriate test cases to this. Okay, so something like that with simple legacy techniques, it is possible to do verification also. That is what we will learn here. But next module is about detailed verification in depth, what is happening across the industry today. From last 4 or 5 years, what are the major verification styles, verification methodologies which got evolved, like using system verilog, using object-oriented mechanism in system verilog for verification. Okay, instead of trying to see verification as a kind of code, people are trying to see it's a verification objects, verification components they call it as. Okay, and there is a notion which has come up in last few years called verification IPs. There are so many companies which are developing verification IPs. What do you mean by it? See, that particular IP is not for any ASIC flow. It is not going silicon. That IP will fit with your module and will allow you to do verification very robustly. Okay, that's what. So we want about the full course. Okay. Now going back to